Okay, so let me just, set the stage here. We're going to talk about, I'd say, more humanoids than quadrupeds. If you remember, like the first day of class, I said, roughly speaking, people are using imitation learning for manipulation. They're using RL for quadrupeds, and they're using model-based things a lot. It's not exclusive. None of those are exclusive. Model-based for humanoids. So I'd say we're going to take the model-based view today, and then it'll work for humanoids and quadrupeds, but I do think that RL has had a huge impact on quadrupeds in the last year or so. Okay, we've developed this nice mathematical framework, right? We started with hybrid dynamics, right? So for so far, our walking framework, roughly, we had to deal with hybrid dynamics. For making and breaking contact, right? Okay, and then we had to deal with stability, which we did with thinking about limit cycles as our orbital stability, right? But given those modifications, which brought some complexity with them, we had to do LQR differently. We had to do everything a little bit differently, but the basic playbook still worked, right? And we've gone this. We worked well for a handful of these models, right? So we started with rimless wheels, and we built up compass gate and need walkers, and we now know how to do trajectory optimization, hybrid trajectory optimization. We know how to do hybrid LQR. I alluded to, but didn't really cover the hybrid, the Lyapunov, right? Sums of squares stuff, but that all goes through. But as we keep going sort of to the right here, it seems like we can just add more and more degrees of freedom. Suddenly we get, foot, upper body, torso, all these things, right? We're just adding more and more complexity. And although the math works, the solver is going to have more and more trouble, I think. It gets harder and harder. These are tractable. We're seeing people solve them. Boston Dynamics is solving them at a very high rate for seemingly the whole set of equations, okay? But it does feel like the problem's just getting arbitrarily harder, which is a little bit at odds with the fact that humanoids have been walking well for a long time. So something's wrong with what I'm saying here, right? There has to be something that makes it easier again. And there is. And that's the number one message I want to send today, is that actually when you get enough degrees of freedom, things get easier again, because you can start making some abstractions. Okay? You can sort of assume that I can put my foot anywhere to begin with, and then fill in the details because you've got enough joints to figure it out later, right? In these walkers, the location of the foot is intimately connected with the joint angles. And there's hard constraints on where the foot could possibly be because of the joint angles. You've got enough links between you, you can kind of say, I'm going to put my foot somewhere around here, and I'll figure out all those details later. Okay, so we're going to work that through in a couple different ways. But the key message is that, as we get highly articulated, lots of links, something gets easier again. I want to make sure we understand that. Okay, because for instance, you've seen all the Atlas videos and all the humanoids that are putting videos on YouTube all the time now, right? But this is actually a pretty old robot. This is around the turn of the century. This is Asimov walking beautifully, right? It's an extremely good robot. And in fact, the technology that grew up around Asimov is still being used on a lot of, not all of the humanoids, but I've watched them enough, I can eyeball it, and I can have a pretty good guess of which control system approaches they're taking. And you will be able to by the end of the lecture, hopefully, too. Okay, so the key idea that made Asimov work even before we had awesome nonlinear optimization and everything, right, was that we could simplify the dynamics roughly of the hip, or the center of mass more generally, from the dynamics of the joints, okay? And we're going to try to see that. Now, I really like trying to sort of separate out the complexity of that full humanoid problem with the sort of essence of the problem with a simple thought experiment. Maybe you'll like this, maybe you'll hate it, okay? So imagine, especially lots of you guys are into space, so maybe you'll like this analogy, right? So imagine I have a spaceship, okay, with some thrusters, and I'm going to put thrusters in weird locations just because it makes my story a little better. Okay, so let's say I have just even a single rigid body satellite. I'll give it a mass and a moment of inertia. I'll parameterize its position. We'll just live in the plane right now, okay? And I'll say there's an angle theta, okay? And the thrusters are applying some force to move this thing around, okay? We're going to identify the configuration of this thing. I'll put theta first for reasons that will become clear later. Okay, I'm going to write Q is just theta, x, and z. And I'm going to call this just force 1, force 2, force 3. We're going to get a little bit more notation heavy in order to get this right in a minute. But this is just kind of a very basic thing. You could imagine if I wanted to write the equations of motion for this, we'll do that real quick. It's very easy, okay? And if you wanted to do planning for this, then certainly the toolbox that we've already developed could do this very well, right? It is still a nonlinear optimization. We've got sines and cosines flying around, okay? But this is definitely in the wheelhouse. Okay, so let's even do the equations of motion real quick right now. And I have to introduce a little bit of extra notation. This is sort of like in underactuated, I get through every chapter except for the humanoids chapter without the heavier multi-body notation. This is the one time where I kind of have to put a little bit of notation up because we're dealing with lots of links and lots of different kinematic frames and things like this, okay? All right, so I'm going to define, there's a handful of sort of interesting points. I'll call this body B, okay? So there's a few points in space that I'm going to care about. I'll call the B will be the center of mass. I'll even sometimes write center of mass location of the body, okay? The position of the body. And then I'll call this, I'll call these points on the body here where the forces are being applied. Actually, yeah, B1, B2, and B3. These are just points in space. So think of these as they live in general, they'd live in R3, but since we're living in the plane, they live in R2. Okay? I'm sorry, those are just abstract points. Sorry, I didn't say that. Pretend I didn't say that. The positions of the points which I'll write as like the position of B1, for instance. That's what lives in R2. Okay. And I'll, in general, need to write things that specify what frame these things live in. So we have this sort of heavy notation in Drake. You might have seen it a bit. It's super useful, but it's a little bit, it's the only way to sort of get through the math we're going to do today. But in general, we write positions with two superscripts and one subscript around it, where this is the position of A relative to B expressed in frame C. Okay, I'm not going to dwell on this, but I think I'll just put enough that you'll see why I put a few of those notational scribbles up. Okay, so this would be, for instance, if I were to write position of B3 relative to the body, okay, I could express that in a world frame, let's say. or I could express that in a body frame. And those are just different choices of how I define what, which direction's up, which direction's associated with X, which is associated with Z, for instance. And that vector, B3, that would be the vector from, one more color here. This is the position of B3 relative to this B, the body origin here, okay? And then that is a vector, okay, an abstract quantity. If I want to write it down as two numbers in R2, I just have to pick a coordinate system to express that in, okay? And that's what, I could either do it in the word coordinates or I could do it in something that rotates with the body, okay? Slightly heavy notation, but it is super important. And similarly, I can talk about the forces as being expressed in some frame, okay, and applying force at a particular location. We add superscripts and subscripts to do that on the forces too. Okay, having done that, then the dynamics are actually pretty easy of that spacecraft. Everything gets more interesting in 3D, but in 2D they're really simple. Okay, so the X double dot is just going to be the sum of the total forces being applied, right, in the X direction. So if I choose to write the sum over all the different forces applied at the different locations, okay, if I express it in the world frame and I take the X component, then this is easy. The dynamics are just the sum of the horizontal components of the force. Gravity vector, then that's the only thing that changes for the z-axis, okay? And then for the orientation, we're going to have some sort of a cross product, right, that tells me how that force turns into a moment, okay? And this is how the notation helps. It's a simple cross product if you write it in these coordinate frames. Okay. So let's just compare that for a second to one you've already seen before. We had the planar quadrotor before, right? It's got to be almost the same. I've got a single body for the quadrotor. I had propellers that were applying some thrust. Okay. In this case, I had something similar, but I've got a sine up here and a cosine here, and it looked nice and simple here. So what's the difference? Just to make this land, right? So in this case, I assumed that U had to be, it could only move in the direction in the body frame like this. In this case, I've got force that is parameterized in the world frame. Okay. If I wrote the forces in the body frame, then I get a sine theta here to map it back to the world frame. Okay, and that's what I've done here. Here I just wrote the forces directly in the world frame, which is just a little easier. Somewhere you have to do that conversion, but in the equations to keep the analogy strong for walking, I kept this in the world frame. Okay, and then here, this one used to look linear and simple, but this one actually is where the sine and cosine. Of course, you have to have sines and cosines somewhere in here, otherwise it's not going to work. It's hidden in here because the position of this body in the world frame is actually depends on theta, because in order to express the thing that's constant is the position of the body relative to the contact point relative to the body, let's say, expressed in the body frame. This would be a constant, you know, if I said that my thruster was in a known location on my aircraft. But since the satellite is tumbling or whatever, then the position, this one here, position of the world frame, actually depends on theta, which the rotation matrix away based on the tumbling dynamics of the satellite, okay, of this thing that's a constant. The exact details don't matter. I just want you to sort of, I'm going to use some of these notations, so I kind of want you to get comfortable with it. This is what it looks like if you parameterize the inputs in body frame. This is what it looks like if you parameterize them in world frame. Okay? All right, so then if we can parameterize this in the world frame, then we've got actually linear dynamics up here. And we have a sine theta, cosine theta inside this rotation matrix. This is the rotation matrix. So we have nonlinear dynamics there. Cos theta, sine theta, negative sine theta, cos theta kind of thing. Okay. So this is nonlinear. If you kept the angle relatively flat, or you linearized around a small angle, then you could actually solve for trajectories of this system with linear MPC, linear trajectory optimization. You could do LQR, right? And if you start embracing larger turns, then we can just use your nonlinear control toolbox. Okay. Now let's make it more interesting. We still have our satellite, if you will, but I'm going to start putting constraints. Okay, this is a weird game to play, but you'll see where I'm going. Okay, imagine it was somehow I don't know, you had to suck up some some resource, natural resource, in order to produce force. Let's say there's only a few places in space where if your thruster happens to be there, then you're allowed to produce force. Okay, the dynamics aren't any harder. Okay, but if I'm going to do trajectory optimization on this, I suddenly have to do more planning. I have to think about, getting to places. You can imagine sort of like, I have to like get to places where I can apply force in order to get farther in the game, right? That's a sort of an interesting thought experiment. So what would that look like? If we had sort of a satellite with regions, let me say thrusters with regions. Well, that starts you start putting constraints on the admissible input. Right? And if any one of these regions is simple, it might be that this constraint can only be active if you're inside some location. This could be like a polytope in space. You could make it it could be a simple condition that turns on and off. But as soon as you have multiple regions, it gets hard again, because it's the same sort of disjunctive constraint we talked about being hard before. If you have to say, I'm either in this region, or this region, or this region, right? Well, even if any one region is a convex set, being in the union of these different regions is not a convex set. Okay, so we get to a much more complicated optimization problem. If you have to suddenly make a discrete decision of what regions I'm in, plus the continuous decision of how much forces to apply. Okay? But you could still sort of imagine trying to work on the problem on a problem at that level of abstraction. It's kind of, you can imagine we're going to need a little bit more optimization, but we could do that. And okay, you could imagine that if someone tells me a priori which regions I should visit in what order, then that could make the problem easier again. That's going to be like when we gave a mode sequence to the hybrid trajectory optimization. If you were to decide a priori which regions to I said step in, okay, so to step in, then the problem gets easier again. Okay. It'll all make sense now, I hope. So now imagine I'm a robot, a walking robot, okay, and I've got, let's say, massless legs, okay. See if I can draw a really cheesy walking robot here, okay. Let's say I've still got my mass and inertia up here. Okay, I've got the x, z position of this, right? Got a theta angle too, right? Suddenly I've got a ground to step on, okay? And I've got forces that are going to be applied by pushing on the ground or the ground pushing on me in the frame of the robot, okay? Now let's assume for a second that I have massless legs. Okay, now can you see where I was going with that, right? Suddenly, you have a center of mass that is going to be moving through space and maybe tumbling through space if the angular terms matter, okay? And the way that you get to move that through space is by making selective contact with the affordances available, the ground, possibly handholds, other things like this, okay? Only when you are in contact do you get to turn on your actuators and apply force, and even that, your force is only going to be typically, if it's a foot, you're pushing down, you have unilateral force. You can't pull on the ground unless you're wearing suction cups, right? Okay, so you have a bunch of different constraints on your forces, and the name of the game is really to take your center of mass and kind of find a way to hop along, pushing when you have opportunities to push, making sure you have another foothold as it goes. This is the fundamental problem of walking, I think, right? Is to make those discrete decisions, plus all the continuous decisions required to regulate your dynamics, and combine those into one set of decision making. We didn't talk about that like that with the compass gate, because your decisions about where to put your foot are just a simple function of theta, and they're so constrained. It's like only what theta could possibly do, right? But once you have enough links, you can start separating out that decision of like, where am I going to put my feet? Where am I going to put my thrusters? You know, where am I going to do foot placement if I'm a quadruped? From the motion of your center of mass. And you put loose constraints, saying that my foot isn't like 10 meters away from my center of mass, okay? But that tends to be good enough. And then you can fill in the details of what you do with your leg to make that foot be in that position in a final pass. That's the big abstraction that makes things easier again when you go to humanoid level stuff. Is that okay? Ask questions about that analogy. Does that make sense? Okay, second major point. I motivated that with saying massless legs, but it's not just for massless legs. It turns out even if you have inertial, heavy legs, that all the math still, this abstraction still holds. I'll leave that here for a second. Okay. And to do that, to see that, what we're going to do is, even if our robot has lots of, has appendages that you're going to use the appendages for stability, you can still make this assumption, okay, But the way you do it is you instead of writing the coordinates of a particular body and asking about how it evolves, you're going to take a quantity like the center of mass of the whole robot and ask how the center of mass evolves. Okay? So to see that, let's just define the center of mass first. Okay. Center of mass is of the, let's say, of my whole robot. Center of mass, CM. Okay, I can put it in whatever frame. I'll put it in the world frame, express it in the world frame here. The center of mass is, you probably have intuition for what it is, right? So it's the center of mass of all my individual bodies, okay, weighted by their individual body I, CM, by mass of body I. It's like the average position of the mass, right? So if you have lots of points, the center of mass is just the weighted average of those points. And if you have lots of bodies, similarly, the total center of mass of the whole thing is the weighted center of mass. Okay? All right, now let's think about how to generalize the dynamics here into the center of mass dynamics. It turns out that if you just write the x center of mass of the whole robot, then guess what? It's still the sum of all the forces applied on different bodies, okay, expressed in the world frame, the x component. No matter how complicated your robot is, no how much your legs move, your center of mass is still going to only accelerate if you're applying horizontal forces. Okay. Same for z, of course. This m is the total mass. The interesting one is the orientation. Okay, we have to think about how to get generalized orientation, and you can. Okay, there's a natural thing, but it turns out we'll tend to want to regulate not only the center of mass, but also some notion of orientation. And the way we're going to do that is to think, even at the rigid body case, about angular momentum. So let me work this up in a second, so in a few steps here. We want to think about something called spatial momentum. How many people know spatial algebra for dynamics? I think it's not very common, but it's, unless you've written a dynamics package, then you know it intimately because it's super useful. It's the only way to get through all the 3D quantities, okay? Basically, for any quantity that has a spatial term, typically I think of them as being in 6 dimensions. If we live in the plane, they're going to be in 4 dimensions. But let's say I have a spatial velocity, for instance. A spatial velocity, I can write the velocity of my point B relative to A, like this, expressed in C, for instance, okay? This would be a spatial velocity of B relative to A, expressed in C. The spatial velocity is just the angular velocity of the point with the translational velocity of the point. Okay. So often, this is 3 by 1 and 3 by 1 vector to give you a 6 by 1 total vector in 3D. But in the plane, I just have one rotational component, theta, and 2 Cartesian coordinates, so this is a 3 by 1 in 2 dimensions. And it turns out all of the physical quantities, almost all of the physical quantities you care about, have a sort of a spatial form. So a spatial force has the torques concatenated with the translational components, the Cartesian force, right? A spatial momentum has the angular momentum and then the linear translational momentum. Okay. So the spatial momentum here of let's say, B about the center of mass in frame W here, which depends on the total velocity of the system. It turns out that the spatial velocity is a 3 by 1 vector, and it looks like this. For a single body case, I can write the angular momentum and the linear momentum. And what you need to think about when you think about those equations is that those equations are actually the equations that just say L dot equals the sum of the forces. If you like, if you're more from a physics background, then you'll appreciate this version of it. This is the time derivative of the momentum is just equal to the sum of the forces. That's true in purely linear terms and in the translational terms, but it's also true in the spatial form. This is a spatial force, which includes the moments and the translational, okay? And there's this is the spatial momentum. So those equations there that I derived in that form could have been written exactly as L dot equals the sum of the forces. Yes?
Why do we write B/BCM?
Yep. It's not either of them. There's a surprising amount of work in the notation to make things clear in every possible case. And in this particular case, you need to say it's the what are you taking the momentum about of? It's the body B. And what point are you taking it about? You're taking it about the point, the center of mass of body B. Yeah. Okay, so if you think of these dynamics as simplifying to the spatial momentum equations, then the natural generalization of, what do we do for the full humanoid, let's say? We're going to control its center of mass, and we're going to control the angular momentum. What we really want is that these equations are the L dot of the entire robot relative to the robot's center of mass, okay, expressed in some frame. They're going to depend on Q dot, okay, and Q double dot even, equals the sum of the forces. This is a way to generalize those equations into something that has the center of mass dynamics plus the angular momentum dynamics. And it turns out that even for, computing the left-hand side is a complicated set of equations, but the dynamics in the center of mass frame are super simple. Okay. There's some work being done by the notation here. Like when I say that I've got the spatial force in the world frame, it has that cross product sitting inside it in order to write the spatial force properly. Okay. but the generalization is like this. So what we're going to try to do is, instead of reasoning about just a point on the body, we're going to reason about the center of pressure, or center of mass of the robot, and the total angular momentum of the robot relative to that center of mass. And that's a simple function of my ground reaction forces. Okay? Even when the robot is doing something like this to recover, okay, it turns out that the dynamics of the center of mass, I mean, nothing you can do here, unless it's creating a ground reaction force, is going to change the trajectory of your center of mass. Right? And similarly, the total angular momentum around the center of mass. Okay, so this is like the new abstraction. Now, otherwise I have these dynamics, and I have a bunch of constraints on when F can be non-zero. Right? When I'm touching the ground, I can push. When I'm not touching the ground, I can't push. That's the essence of the problem. There's one other thing we left out, right? In the walking robot, in the compass case and everything like that, we talked a lot about the impulsive collisions, right? We said that there was energy lost every time your foot hit the ground. In the humanoid case, people mostly ignore that. That's not purely justified, but it's kind of almost justified, okay? And here's why. So if I'm going to regulate my center of mass, and I say the acceleration of my center of mass is actually 0, or my center of mass velocity is 0, which is what a lot of these robots do when you see them walking around like this, okay? If your center of mass actually keeps 0, doesn't accelerate vertically, then that means in order to achieve that, you actually have to set your foot down so slowly that there's no impact, right? And you can do that. If you have enough degrees of freedom, you can actually do that. No matter what speed you're coming in at, you can like start lifting your foot right before you touch down to basically touch with almost 0 velocity. Yeah? Yeah, there's well, I would say he always looks like he's squatting, right? Yeah, this is, so why do the robots walk like this? There's 2 reasons. I think one, it makes the math easier, right? You can ignore impacts, and actually small angle assumptions. You can do a lot of planning with linear dynamics. The other one is that the assumption that you can move your feet is better when you are not at a kinematic singularity. As soon as your leg goes straight, then you have more constraints on what you can do with your feet. So to separate those out, we squat a little bit. We pay a huge tax in terms of energy to do that. Like, you walk around like this for a little while, you'll be pretty tired pretty fast. Yeah. Yeah. I believe that when you're playing sports and you want to be ready to be doing anything. Yeah, that's, I think, a generous interpretation of what they're doing. But my robots had their knees bent too, so yeah, I'm not going to throw stones. Okay. I want to make sure that the high-level thread. So robots got easier because we could separate foot from center of mass dynamics, right? And we can sort of keep that abstraction. And there's a natural analog of a single body moving through to the whole dynamics of the robot. Okay? It's just controlling the location of the center of mass and the total momentum around that center of mass. And you have to pick a frame for that. World frame is the common one. Okay. So that seems complicated. Then the question becomes, how do you actually do that? Traditionally, before we brought in all of our optimization tools, people did this in sort of 3 stages. The first stage would be to plan your foothold separately with a pretty heuristic method. Let me actually write this down. Okay, well, I'll tell you what ZMP is in a second, but the class stands for zero moment point. I'll help you understand what it means in a minute. Okay, the standard recipe sort of goes in 3 steps. First step is we plan some footsteps. It's kind of like picking the mode sequence. Okay. Traditionally, this was done very heuristically, right? And we've sort of moved towards solving nice optimization problems. Kind of to pick the footsteps. Okay. The second step then is to plan the center of mass trajectory and angular momentum. Okay. And then the third step is to fill in the details, plan the actual joint angles. The center of mass and angular momentum, because these equations become very simple, there are some cases closed form solutions to go from footstep planning with some restrictions, and then there's optimization-based ways to do this. Okay, and the last step is actually fairly simple. It's just solving kinematics problems to turn your foot position and your center of mass position into new foot positions. And then when you go to execute with something like people will call them a whole body controller, which just sort of is a generalization of like a position of a simpler controller here. So let me walk you through those pieces. And by the way, this is actually a very, very general recipe. So I was supposed to put that up when I said angular momentum was conserved, right? But this is a pretty general recipe. So this is kind of how it played out when we were doing the DARPA challenge. We actually had a perception system that would use the LiDAR. We didn't really know how to use RGB super well back then, so we were using mostly LiDAR. Okay, we would identify patches in the terrain that seemed to have similar normals. Okay, we would segment the terrain into places you could potentially step, right? And then we had this footstep planner that if you watch, it's just drawing its planned feet positions. Okay, and then we have the center of mass trajectory above it, and this will go again. More interesting when it gets on the terrain. Small pause. Thinking time, right? But to be fair, like if you fell down, it was really bad. So we were like, I'd rather be embarrassed and think too long and make sure we do the right thing. Oh, the movie stopped. There's a second part of the movie that's even better. Oh, yeah. Anyways, that's kind of how it plays out. And this is a general recipe. I remember, so I gave a talk at the Humanoids conference way back in the day. I was like, this is how we should be thinking about about robots, even for parkour. Right? First, you plan your contact positions and your center of mass dynamics, and then even when you're doing parkour, right, you fill in the details later. Yeah.
Is the computation all happening on the robot?
The story was a little bit complicated in the DRC. It was meant to be shared autonomy with a degraded network link. So you had a computer on board. That was most everything was on board, but you were allowed to have a network connection to a human operator, but it was when you go in the building, it could drop out. It could have long latencies and stuff like that. So it was trying to reward teams that made more autonomy, but allow fallback to human control. So most of all that planning was happening on the computer in the backpack, or in the belly actually. Okay, so then how do we let's say well, I won't talk too much about the simple version of footstep planning. The simple version would just be kind of like you could imagine a recipe saying, I'm going to move my left foot first, my right foot first. I'm going to move it this far forward. If there's terrain, I'll shift it around. And that kind of the very simple, like first thing algorithm you'd write solves a lot of the basic, almost flat problems. And you have to get smarter when you have more constrained environments. Okay, but let's just say I come in with a nominal footstep plan. Let's just assume some someone clever wrote a nice footstep plan saying you're going to put your foot here and your right foot here, left, right, right, and gives me this sort of simple plan. It's actually pretty fun to write these. We got better at doing them over the course of the DRC. The final one was all optimization based and pretty elegant. This is the footstep plan, kind of plus center of mass plan for Atlas walking through the door. Robin Dietz was the one who did this. He first did the manual footstep planning for walking through the door, and he's like, that was the worst experience of my life. I'm going to solve this optimization problem and never solve it again. Because Atlas, I don't know if you guys would remember Saturday Night Live, Hans and Franz. I always think of Hans and Franz when I think of Atlas. They're like these guys that pretended they were super buff. They're like, I'm too buff to get through the door. And so I have to kind of walk through the door like this. Well, that's Atlas, right? So you get up to the door, and Atlas is just like too wide to go through a door. So just a normal door, you have to walk through sideways. And it was a nightmare for footstep planning, okay? But we had pretty good algorithms that would do that by the end. So the question is, how do you go from a footstep plan to a center of mass plan, right? And this is where the cleverness comes in that I think is worth sort of understanding. It turns out that there's an intimate connection between the center of mass, intimate connection between center of mass dynamics and center of pressure dynamics. Okay, so these equations that I wrote, where you say that the total dynamics are just the sum of the forces, are absolutely correct. But the sum of the forces can be summarized as a single force operating from a single, you can sort of summarize the accumulated result of many forces at a single point with a single force. Okay? Forces all add beautifully, right? So we'll define the center of pressure. Make sure I get my notation right here. The position of the center of pressure in, let's say, my world frame here is, again, a weighted combination of my different ground reaction forces. It's basically the force equivalent of the center of mass. Yeah? I'll put them all in the world frame. Okay, so I'll take all the locations of my contact forces on my foot here. You're going to work through these equations in your P set. Okay, I've got my foot. I've got a bunch of forces coming in, right? So I've got force 1, force 2, force 3. Okay, I can summarize the total effect that that has as a force and a moment, actually, right? Force, center of pressure, let's say, and plus a torque, potentially. But we'll define the center of pressure as just the weighted average of these forces, okay? And it turns out that if you were to recast these potentially complicated equations with position cross force, sitting inside here in order to make these equations. If you write things in terms of the center of pressure, then actually these equations simplify beautifully, okay? And you get a very simple relationship between the center of mass dynamics and the center of pressure dynamics. I'll write it with the x and z because it'll be cleaner here. Xz double dot plus mg. Okay. This is just saying that this is the center of mass, and this is the center of mass here. Then the dynamics, if you write them in the terms of the center of pressure, simplify to something very simple. Okay, one simple set of equations. And this is maybe the fundamental insight of ZMP walking. It's interesting. If you think about those early walking, and still actually a lot of the walking robots today, there was a debate at the time between whether you needed force control in your legs or whether you could get away with position control. And the Asimov-style walkers actually used only position control in the legs, and they basically said, even though my goal is to control my ground reaction force, there's a simple relationship between my center of mass dynamics and my ground reaction force. So if I control the kinematics of my center of mass dynamics, then I'm actually controlling my ground reaction forces. Okay. So when you don't worry about impacts and you don't have to worry about uncertainty in the ground, position control seems to be enough because of this sort of very simple relationship. This simple relationship is clean and good when the terrain is flat. Okay. When you start getting into and you're only pushing up on the ground from the ground is only pushing up on you. When you start holding handrails, you have to generalize this to slightly more complicated equations. Okay. So the center of pressure and the center of mass dynamics are intimately related. And in fact, this it looks like a non-minimum phase system. So if I want to move if my center of pressure is too far forward, then my center of mass will start falling back, of course. If I actually want to, I want to control this, I can move my center of pressure back in order to get my center of mass moving forward. So here's how so understanding this relationship, which you'll work through the actual math that gets that on your P set, this is the basic idea behind the ZMP walking. We're going to program in, given the footsteps, a very simple trajectory of the center of pressure. Okay, this is going to be my center of pressure trajectory. Okay, we need a schedule of our feet over time, and we're going to need a schedule of this over time. But roughly speaking, I'm going to plan that at some moment, my center of pressure will be exactly in the middle of this foot. When that happens, I'm going to lift this foot over. Okay, I'm going to put it here. I'm going to move a straight line between the other foot. I'm going to move it there. Okay. Very simple recipe. As long as the center of pressure is inside the convex hull of the support polygon, this is called, okay? As long as the center of pressure is inside that support polygon, then it turns out you have some notion of stability. They call it the ZMP notion of stability. Okay, so basically you won't fall over your foot if your center of pressure stays inside your support polygon. Okay, and so I'm going to think of this as my support polygon, and then once my ZMP lands inside this foot, I can lift this foot up, change my support polygon to be this. Okay, and I can choose a straight line like this. And that's what I want my ground reaction forces to do. I want to move my ground reaction forces over to here, move my ground reaction forces over to here, move my ground reaction forces over to here. Okay. Once you have a preordained schedule for the center of pressure trajectory, then actually the center of mass trajectory plays out naturally given those equations that I wrote here. Okay. You can actually basically solve for what the center of mass trajectory has to be from an initial condition by noting the simple relationship. Yeah. Center of mass? Oh, this one too, yes. Thank you. Okay, so I can go like this. Basically solve for what the center of mass equations have to do in order to get this. And it's actually very interesting. So if you just run those equations, okay, and you were to plot a slow trajectory, which really puts all of my my pressure onto this foot, and then picks up and puts all my pressure onto this foot, then what you'll see is that in order to do that, your center of mass actually has to kind of go over this foot, and then go over this foot, and then go over this foot, and go over this foot. Okay, and that's a very conservative style of walking. That's what happened back in the day. You actually didn't pick up this foot until your center mass was safely over that foot. Then you lifted up this foot. Okay. But if the timing on your ZMP trajectory, your center of pressure trajectory, is faster, then actually you can achieve this with a center of mass that never even goes over your feet. Okay, and you get a dynamic gait. Right? You get dynamic walking, meaning that your center of mass is not, you're always falling down effectively, okay? But you can catch yourself and you get these trajectories that are much straighter. When we were making Atlas Walk, we started naturally trying to make slow gaits, right? And it was so hard to get that robot to walk. Right? It was really, really hard. And then one day, we're like, let's just see, we were pretty happy with it. Let's just see if we can make it walk a little faster. And it's so much easier to walk fast than slow, right? Because once you walk fast, your center of mass doesn't actually move that much. So you're not actually throwing that much energy around side to side. And the faster you walk, the straighter your center of mass. And you just have to do a little bit. And it's actually much easier to walk fast than slow. It requires less lateral motion. Yeah. Okay. Okay. And you think that's because of it'd be interesting. So he says that humans have more instability or less stability at slow speeds also, yeah. Probably they have a larger center of mass deviations also. Yeah, I would guess that those are correlated. Right? Yes? Yes? Okay, so I'm sorry I said it too quickly. So so imagine I have 2 feet on the ground. Then one thing I know for sure is that the center of pressure has to be inside these, because these are the only places, when I'm walking on flat terrain, these are the only places I have external forces. So the average force is absolutely going to be inside the convex hull of this force. And the center of pressure, therefore, has to be inside. If the center of pressure is completely inside this support, then you also know that you cannot be tipping over. Your foot cannot be tipping over. Okay, so what we want, first of all, is just to think about when 2 feet are on the ground, I can move around back and forth as long as my force doesn't go to the edge of the foot. I know if my center of pressure is inside, the average force is inside there, that I must have some amount of forces on this side and this side that are compensating. It's only if my center of pressure gets exactly to the edge that I tip over. Okay, now to your specific question. So I'm going to think about a sequence of support polygons, right? First, I'll start with, let's say, 2 feet on the ground. So I have this. And then instantaneously, I pick up this foot. And my support polygon becomes just this foot. And until I set it down, I'm on just this foot. And then as soon as I set it down, I have the ability to generate forces from that whole convex hull. Right, so back to my original picture of the satellite. These are kind of the pictures of the things that get generated, which constrain where your forces can come from. Okay, and then once you have the center of mass trajectory, then it turns out you can just solve for the kinematics and play out and get these kind of things. Yes?
Another question about the center of pressure. So if I take my foot off the ground,
Yep.
then I would expect like there to be a discontinuity in the center of pressure. So I would just pretty much from 1 to 1.
You can avoid that by planning. To not have, so basically, if your center of pressure was on the boundary of that foot, or even in the middle, then when you pick it up, something discontinuous is going to happen. But if your center of pressure is nicely on that foot, then you can actually pick that foot up and smoothly, you don't have a discontinuity in center of pressure. Yeah. It does require, in order to achieve that and achieve that, you will pick your foot up slowly. You won't just immediately go pick up, okay, to execute that trajectory. But it's possible to do that, once you have a trajectory that's safely inside the support polygon. Cool. Okay, so that's an abstraction that's still used today. I'll show you some videos of different robots. Okay, it's based on these set of equations here, which are they're a little bit nonlinear, right? They've got center of pressure, times center of mass. They've got a I theta dot hanging off the side here. Okay. It turns out if your center of mass stays at a constant acceleration, actually what matters, but often a center constant height, then basically those dynamics, and you keep your angular momentum small, then those dynamics linearize, and you can do LQR, you can do model predictive control, you can do a lot of planning of your center of mass trajectory using linear techniques. So kinematic singularity is one, and doing linear planning is the second reason why those robots walk like that. Okay, so let's check this out. So let's just look at a couple of the humanoids that are out there now. So when you look at Scott talking about, this is a couple years old now, talking about optimization and control. They talk about the momentum dynamics. That's our L dot, whatever. That's our center of mass plus centroidal momentum dynamics. Okay, plus full kinematics. Okay, so what people have done increasingly now is they started to try to write optimizations that merge those two. So one thing you can do is you can try to optimize your center of mass and some joint angles at the same time. You still use the center of mass dynamics, but you use the leg kinematics. So that's what he says. Centroidal dynamics and full kinematics is the way that they're solving this. So that lets you write tighter constraints about sort of where those forces can possibly come from. And they do offline trajectory optimization for like these complicated flips, and then online trajectory optimization to stabilize. Even if you're doing a flip like this, okay, your centroidal dynamics are correct. They're not an approximation. They're exactly true about your center of mass and the total momentum around the center of mass. Okay. The only thing that you lose by planning in this sort of centroidal dynamics plus kinematics is if you have things like torque limits. Okay? Since you don't have any explicit notion of the forces that are used to create those, or the torques that are meant to create those forces, you can't reason about torque limits. But otherwise, you have everything about the humanoid captured in those equations. And if you have Atlas, then you don't worry about torque limits that much, I guess. Okay. And that is exactly, actually, when I showed, I simplified a little bit when I presented the first time. I said it was just hybrid trajectory optimization. But it wasn't actually in the notebook. If you look at the notebook, it's not actually using the full dynamics of Little Dog. It's writing the centroidal dynamics plus constraints on the forces to do the planning I showed you before. Okay, and we made Atlas run this way, although only in simulation. We were too afraid to break the robot before the competition. There was actually one day, so we were like practicing all these things we were going to do, right? This was when American Ninja Warrior was super popular, and I wanted my kids to like me, so we figured out how to make Atlas do a bunch of the tasks from American Ninja Warrior. Yeah, so the dynamics between Boston Dynamics and MIT during the competition were awesome. They were super supportive. But they did say if you start jumping off boxes, then we will not guarantee we'll fix your robot before the competition. And then one day, they said we're going to replace the arms. So unfortunately, there's going to be a little bit of downtime. You have to ship your robot back to Boston Dynamics. On a Friday, we'll try to get it back to you early the next week. And we're like, dude, Friday morning, we're going to start jumping. That was like the one time where we could afford, we knew it was going back anyways, and we were going to have downtime. So we had done all this work on offline trajectory optimization, and we spent like one day jumping off everything. I don't think we ever stuck the landing, but we had exactly one day to play with it. And that is really what sort of eventually got much, much better, but led to this, right? So my understanding, not official, not sanctioned, but is that they are roughly planning footstep holds and then doing nonlinear model predictive control to complete that. Okay, let's look at a couple of the others, right? So I just pulled these down quickly, right? That looks like a ZMP walking gait to me, yeah? It's smooth and good, but it's, I think, a lot like what Asimov is doing. Interestingly, once you decide to move your center of mass and regulate your angular momentum, then moving your arms around actually just comes out of the equations for free, right? So when you figure out the joint angles that have to be used in order to regulate your center of your centroidal momentum, it actually naturally lets the arms swing. Yeah. Yeah. You're saying that in which way? Mm-hmm. Yep. Well, I think a lot of it is that they're keeping their feet flat, right? So I probably like that, right? I think if you're, I don't know, maybe is that enough to cause it? But a lot of times the feet are flat because you want to have a nice big support polygon and keep your center of pressure inside the support polygon, right? I mean, of course, it's possible to go up on your toe, but then this simple notion of stability is violated. So a lot of the robots are flat foot walking. Yeah? It's good. It works, right? No, I mean, well, let's continue. So I don't know, so I'm safe to sort of say things, right? But right, figures doing something similar. Another thing you notice about these is that they almost all of them have a fixed cadence, right? So they go like this, and then they start moving around, right? And that's because they've somehow separated the footstep planning problem, and at least in the cadence step, from the full dynamics planning, right? When you see that, I think that's a clear indication that they've done that separation. Here's the exception, right? Although it's still a fixed cadence, right? But this is now RL to do walking, at least as the this is unitary, yeah. So it's actually super interesting to ask. I mean, I don't know that looks better. I mean, it looks more robust, but it doesn't look better, right? Yeah. So it looks very RL, right? Yeah. Yeah. Yes. Yeah. Okay. So one of the subtle reasons why I think RL is working well in quadrupeds and in this biped, and maybe not in all the bipeds, for instance, is that when you do have very light legs, like that slip model, then, and your feet are smaller, let's say, then your sim to real gap is smaller because your impacts with the ground are less severe and they don't need to be modeled as carefully, right? And certainly point feet are easy to model in simulation. So I think that is why, I think one absolutely could make, to do the work to make, let's say, Optimus in simulation sufficiently accurate to do RL in simulation. But I think it's easier to do it on these really light feet, like robots. Yeah.
I was wondering, for like Tesla and all these companies that bring their robots, is part of the reason why they first go to ZMP is that's sort of a stepping stone at the baseline walking, and then they start doing other stuff. And it's just so hard to bring. Everyone's sort of homegrown everything.
Yep, I think that is true. I think, but just appreciate like how diverse and general purpose the ZMP walking is, right? So it's one thing to have a policy that walks straight, but if you have any new situation that you want to navigate through, it's pretty easy to write a footstep planner, and you can close the loop. And like to do a completely environmentally goal-conditioned policy in RL that does everything. That's a much bigger ask, right? So it's not just like find a nominal limit cycle. It's like conditioned on all the task-related variables. Yeah. Did you have a question back there? Yep. So the question is, maybe what are the more lifelike? So a lot of people noticed that was a problem and then started working on different ways to get around that. So I've seen robots still using ZMP that had, for instance, an extra joint in the toe. They would tend to have slightly big toes, okay, but you could move into a smaller support polygon on your toe. That was a good idea. I've seen people add hip joints so that you can, even if your leg is straight, your hip can can give you something that avoids the singularity. I would say that the Boston Dynamics Petman video from back in the day, it was actually a robot that was designed to test like chemical suits. It had red tennis shoes on, if I remember correctly. Was probably the most natural gait I've ever seen still to this day. And it was, I think, just because they weren't explicitly using ZMP, although all the ideas were pretty similar. They're still doing footstep placement heuristics, but yeah, it was I think that was my favorite, most natural gait ever. Okay, the last step, of course, is making once you have a plan, you have to make a controller that stabilizes it, okay? This was our balancing controller for Atlas, tested very late one night after we were sleep deprived. I was off screen laughing hysterically because I hadn't slept in like 3 weeks. And that was us trying to get out of the car. This is N9, if you've ever seen MIT N9. It's kind of not a great place to work, but it was good for robots in possible hydraulic spills. So it turns out that actually fairly simple. So we weren't doing LQR in this. We're doing kind of the one-step version of LQR that was trying to regulate the nonlinear dynamics, but everything's simple when you're just doing one step. And you can write a small quadratic program, basically, that balances the robot and gets the job done. Except on the day of the competition where you fall down once. But no, it's a pretty darn good controller. Yeah, I think I will skip since we're at the end of the time, but I'll skip the details. But it's actually a very straightforward derivation, given everything we've seen, of a one-step version of the controller. Okay, so the big step that we've kind of not done yet, that we will talk as we continue to talk about motion planning, is if we wanted to avoid having to a priori set the footsteps, and you wanted to jointly plan, where do you have to put your foot, and how do you move your center of mass dynamics? That's the big piece we haven't done yet, and we will do. And the graph of convex sets, for instance, is a good way to do that. It's a new good way to do that. But I won't do that in the last few minutes. Let me instead show you the quadruped version of the story. Yeah. So I do think RL has made a huge difference in quadrupeds, and this is the one that I think really got people thinking about that. This is work from ETH, Marco Hütter's group, training and simulation, rolls out in real, and it's just incredibly robust. Right? This was the first major success story, I'd say, in quadruped locomotion. Everybody took notice, started trying similar things. I think RL works partly because the sim to real gap might be smaller. They also did a lot of work in theirs in that project to model the actuator dynamics to make the sim to real gap small. Okay, but incredibly successful. And nowadays, we're seeing more and more like just awesome. Like that is still one of the coolest things I've seen. This is Unitree a few weeks ago, yeah. That would have been hard to plan with these techniques because torque limits, for instance, matter. All the limits of the robot matter. So the abstraction of like being able to place your foot independently of the location of your body just doesn't work anymore when you're right at the dynamic limits of the robot. And of course, Boston Dynamics announced one the other day where they could do similar things. I think they've actually released this on Spot 4.0. I haven't actually seen it happen on my robot yet, but yeah, pretty amazing stuff. Okay, so high level, when you have enough degrees of freedom, things get easy again. And there's a pretty good recipe in the zero moment point, and you can actually push out on that and I think relax a lot of the assumptions. And that's what people have done, is slowly kind of, instead of separating out footstep planning and center of mass and joint angles, they're finding ways, like in Atlas, to jointly plan all of them, okay? And we'll talk about the optimization way to do the discrete plus continuous one in one of the next lectures. Okay, oh yeah, any question? Yeah.
Why do you think Atlas decided that ZMP and Fragile was more appropriate for like the smartboard than
Okay, so to be clear, I would say Atlas is one of the ones that's not doing ZMP straight up. They are still doing planning with centroidal, but ZMP is, well, let's see. The ZMP model is most clear in flat terrain and modestly off terrain, and it uses those as simplifying equations. I think they are solving the full centroidal dynamics equations, so not using the ZMP simplification. But I think that's a recipe that's worked extremely well. So in my mind, when you have good models, then model-based control is going to do extremely well. The thing that happens in RL that motivates this is that when you go into unknown terrain and you are relying on your perception system, that's when we do have really good models of our robot. We don't have really good models of the environment. When you start going into more and more diverse environments, that's where model-based control starts to fall down, and learning-based control has been doing better. Okay, and RL is the one that's working for quadrupeds right now. Yeah.
Is that because the constraints and such of the environment become too difficult and uncertain?
I think so the traditional model-based pipeline, and we will talk more about this explicitly, but the traditional model-based pipeline, the first step is to estimate the state of the environment. And then we can do model-based control. That is overly brittle. If you instead train, let's say, or even take a known controller in simulation, a model-based controller that knows everything about the environment, but then you map it over into a big neural network that goes directly from pixels to torques, then you can avoid doing explicit state estimation and do better in more complicated environments. Yeah. That's another thing that I think is the reason why quadrupeds have been working well. I think the success story of RL in ETH, for instance, was that a relatively simple parameterization of the environment. Like if you've seen this Isaac Gym kind of, they walk downstairs, they walk on a few different terrains, and it seems that if you're robust to those terrains, then you're robust to whatever you end up finding in the real world. Right? Which is relatively easy if you have point feet that make light contact, right? When you're imparting a lot of energy, then the contact modeling gets more complicated, but if you have light distal feet and point contacts, then that's pretty easy. We haven't seen the same, we haven't seen the same success for humanoids yet, and for more complicated manipulation, there's people that do things, but there's a lot of, that's not as good of a strong of a workflow. Cool, okay. See you next time.